Video 6-4, covalent bonds, properties of molecular compounds. Okay, so, covalent bonds. Okay, what happens when we have a covalent bond? Okay, if two or more atoms lower their potential energy, think of this as their internal energy, as they start getting closer to each other, then a covalent bond may occur. Okay, so, if we start looking at this diagram here, two of these atoms separated by roughly this distance here. Okay, they have this amount of energy. Now, you notice as the atoms start getting closer and closer together, the energy starts to decrease. Okay, and they reach a minimum energy. These are both two hydrogen atoms at a distance of 0.74 angstroms. Okay, angstroms is just another weird little unit of distance. Okay, it's basically like 10 to the negative 8th centimeters. Okay. Now, if the atoms actually start getting a little bit closer together, notice the energy shoots way up. So at this point right here, these two atoms would be the most stable. Okay, so they form a covalent bond. Okay, now, what is a covalent bond? It's an attractive force between the nucleus and the electrons of the other atom. Okay, and remember, all your bonds are basically attractions between nuclei and electrons. Okay, now, two atoms will basically start sharing electrons. Okay, so when we started drawing like our Lewis dot structures, okay, this meant right here that both chlorines were sharing a pair of electrons. Okay, now, as the electrons are being shared, each electron does still repel the other one. Okay, but the force of the nucleus attracting this electron and this nucleus right here attracting this electron, okay, causes them to actually stick together. Okay, so in covalent bonds, you have a sharing electrons. Okay, and basically what happens? The orbitals from one atom have to overlap with the orbitals from another atom. Okay, and the bond is not from the sharing, the bond is the attraction of one nucleus to the electron cloud, okay, or the orbital of the other atom. Okay, so it might be a little bit hard for you to see, but the nucleus on this one, okay, and the nucleus on that one will be right there somewhere. Okay, and this gives you kind of an idea of what an electron cloud is. Okay, it's basically just a mathematical interpretation of the probabilities. Okay, and the further out you get, the less dense or the lower the probability of you finding the electrons. Okay, now for each one of these atoms to bond together, okay, or share electrons, the areas that are probable for them to have electrons have to overlap. Okay, so this nucleus attracts its own electrons plus the electrons that are being shared by this one. Same thing here. This nucleus attracts its own plus the electrons that are being shared in the orbital. Okay, not all the electrons are going to be shared. Okay, now, multiple bonds. When you're drawing Lewis structures, sometimes you ended up putting more than one line between two atoms. Okay, so what happens? Sometimes you have to share more than one pair of electrons between the same two atoms. Okay, double bonds, that means two pairs or 4 electrons are shared. Triple bonds, 3 pairs are shared between the same two atoms. Okay, this is not a triple bond. Okay, this is 3 single bonds. A triple bond has to be the same two atoms share 3 pairs of electrons. Okay, in general, in terms of bond energies, okay, single bonds will have less energy than double bonds, which will have less energy than triple bonds, which means when the bonds form, they give off less energy than double bonds. Now, if you want to break the bonds, you have to put in more energy to break a triple bond compared to a double bond, compared to a single bond. Okay. Now, into the lengths between X and Y, if they were a double bond or a triple bond. Okay. The distances, the bond lengths between X and Y in a single, double, triple bond, because of the strength of the triple bond, it holds it closer together. So these will be the shortest. Okay? And single bonds will be the longest for a single, double, triple bond between the same two types of atoms. Okay? Diatomic molecules. What does diatomic mean? Well, di means two, atomic mean atoms. Okay? A diatomic molecule is made up of only two atoms, and since it's a molecule, they have to be covalently bonded to each other. In other words, they're sharing electrons. Okay? Now, there are some diatomic elements, in which case both atoms have to be the exact same. Okay? Now, these elements will not be stable in nature as uncombined atoms. When you write the formula for oxygen, you don't write it as O, you write it as O2. Reason for that is oxygen atoms are very unstable. Okay? They'll either combine with another oxygen atom in a double bond, or they will be bonded to another type of atom, like say hydrogen in water. Okay, now, which elements are diatomic? Simple. Just remember this. Never have fear of ice cold beer. Okay, now, this is a mnemonic device for remembering which elements are diatomic. So, if I said write the formula or the reaction between hydrogen and oxygen, you don't say H plus O. You would say H2 plus O2. Okay? Nitrogen, hydrogen, fluorine, oxygen, iodine, Cl for cold, not Co, and Br, not Be. Okay? Now notice fluorine, iodine, chlorine, bromine. These are all the halogens. Okay? So every halogen, if we say chlorine is going to react with fluorine, it's F2 plus Cl2. Okay? Now, that does not mean you cannot have a single nitrogen in ammonia, NH3. Okay? But nitrogen is not by itself. Okay? Just when these things are pure, they have to be diatomics. Now, properties of your molecular compounds. Okay? Covalent bonds are going to be stronger than ionic bonds. Okay? But molecular compounds, which is where you find covalent bonds, these things have low melting points. Okay? So the reason for this is because when you try and melt a molecular compound, you do not break the covalent bonds. Okay? When you try and melt a molecular compound like water, H2O is bonded to an H2O. Okay? There's an attractive force right here between these two things. But that force there is not a covalent bond. This is a weak force. Oops. Okay, this is an intermolecular bond between two different molecules. So this is the one that you break. If you were to try to break that bond right there, that would be a really strong bond. Okay, and not only do they have low boiling points or low melting points, they have low boiling points. Matter of fact, some of them, their melting points are so low it's below room temperature, which means they will be gases at room temperature. Okay, and unlike ionic compounds, these can vaporize at room temperature. Example, water will evaporate. Okay, these will be poor conductors or non-conductors of electricity and heat. And if it dissolves in water, the aqueous solution will not conduct electricity. Okay, what happens when it dissolves? The molecules that you have, unlike ions, the molecules have no charge to them. So, if it dissolves into water, the molecules are separate, they're free to flow, but they do not have any charges. So, you cannot have an electrical current if the parts moving don't have any charges on them. Okay. Last type of molecular compound we look at, a special type. This is known as a network covalent compound. Okay. Special type where the only type of bonds that you have are going to be covalent bonds. In other words, okay, it's one giant molecule. Now, these have very high melting and boiling points because you want to break it apart, the only type of bond you have is a covalent bond, and it takes lots of energy to do that. So here's a couple examples of some network covalent solids. This one right here, this is basically silicon. Okay, or you can consider it to be quartz. Quartz is made up of silicon and oxygen. Okay, so these are your silicon atoms. These are your oxygen atoms. Okay, and notice every single bond that you see right here is a covalent bond. So if you wanted to break apart quartz, okay, or glass or something like that, which is where you find a lot of your quartz, okay, your silicates rather. Okay, now you have to go and break every single one of these bonds. Okay, this one right here, if you notice, the atoms are all exactly the same atom. This is carbon. When carbon bonds in 3 dimensions like this, the whole thing basically forms diamond. Diamond, hardest naturally occurring substance. Now, you notice this right here. This is also all going to be carbon. Okay? But it bonds only with covalent bonds in 2 dimensions. Okay? The bonds right here, these are weak forces, intermolecular forces. Okay? So this is not going to be a network covalent solid, at least not in 3 dimensions. Okay? This is also still carbon, but this is the form of carbon called graphite. Okay? Graphite is what you have in your pencils. Okay? It's not lead, it's actually carbon. Okay? Now, this force right here is so weak that if you were to pass your graphite over a piece of paper, this part flakes off, then this part flakes off, then this part flakes off. Okay? And what you have is your pencil writing. Okay? Now, a single layer, okay, is actually a new form of graphite called graphene. Okay? And they're finding new uses for this because the single layer is going to be real strong. Okay? And also carbon's a good conductor of electricity, so lots of potential for this material called graphene. And today's review question: what kind of bonds hold atoms together in a network solid? Ionic bonds, covalent bonds, metallic bonds, polar bonds, or nonpolar bonds?